Okay, welcome back. We're going to finish up our lecture today with dynamic memory allocation. I have this as class 21, even though we're doing two of them today. And the reason I separated these out into two separate videos is kind of like we need to switch gears and switch topics, so it didn't make sense to put these together. So even though we're all really still in the one day, we're just doing two of these. So dynamic memory allocation. So let's talk about first a motivation for that. So first off, static allocation is what we've used so far. And what static allocation is, if you think about an array. So here's an example of where we might want to use, well, first off, static allocation, but then we'll talk about dynamic allocation. So notice I created this structure. I'm calling it bullet struct. That's the type of structure. It has inside of it a float for an X position, a Y position. So let's say we're writing a game. We need to keep track of bullets as they're moving across the screen. So imagine like that, that you have some bullet on the screen and it's moving across the screen and we need to track it. So we might have an X and a Y for where it is on the screen. We might have a speed, an angle that it's traveling at. And we might also have a lifetime because we don't want the bullet to exist forever in our world. We want it to go for a certain amount of time and then disappear. So we might have this lifetime that is number of frames and that counts down, and when that gets to 0, the bullet expires. Well, to make an array of those to keep track of more than one bullet at a time, we could do a static allocation like this. And actually I need to fix this code. There's something missing here. We need the type bullet struct. So struct of type bullet struct is what we need to store. So this is making an array of structure of type bullet struct. We're making 100 of them. So that's making an array of 100 of those bullets. So that static allocation, though, by making an array of exactly 100 can be problematic. You might say, well, what's wrong with that? Well, it could be okay, but it also might be problematic. And the reason being that why would that be problematic? Well, the first thing is once the bullet array is allocated to have a space for 100 bullets in it, it can't ever be changed. So once that variable has been allocated, with this block of memory for that array has space for 100 of those structures in it that each have their own X and Y and angle and speed and lifetime, but we can't ever change that. Which means that because it can't ever be changed, there's two things. One is we're either wasting memory. If we don't have any bullets on the screen, why have allocated a giant block for 100? And the other, maybe even a worse problem is if we have 100 spaces in that array, what if we need more than 100 bullets on the screen at one time? We don't have space for it in that array. We might have to have it when you fill that up, you try to fire, it doesn't fire, or you fire and one of the oldest ones disappears. So before I go on, I'm going to tell you a static allocation programming horror story. This is a personal story from my past. That when I was in college, I would like to say hired, but it wasn't that. It was I got volunteered to help somebody with a programming problem. And the programming problem was this, that they had this 5K race as a 5K, 10K race, and they had people run the race. And the problem was back then, the way that they kept track of the winners and losers was people would run across the finish line and they had somebody with what's called a printing stopwatch. So it's like a stopwatch that runs, but when you press a button, it would print out on a strip of paper the time. And the problem being that you have to associate each time with the runner number. So what they would do is somebody would cross the line, they would push the button, they'd pull off the number off of their back, they would stick it on one of those spikes you see at restaurants that they put receipts onto. And so they would do that, and then at the end of the day, or as the race was going on, they'd pull the numbers off the spike, and they'd write the number next to the number that printed out on the printing stopwatch. And so the problem, as you can see, is that they would, at the end of the race, once everybody finished, then they would have to go through the printout from the stopwatch and figure out what number went with what person and what age group they were in and whether they were male or female and whether they ran the 5K or the 10K. And then they would have to compute the results and see who won each age division and each gender division and each race division. And it took them hours to figure out who won each of the things. And the problem was people just ran a race. They don't want to sit around for an hour waiting to see what the results are. They want to go home and take a shower. So I had this guy contact me. He actually contacted someone else and they volunteered me. And they said, hey, there's this guy, Paul. He's a good programmer. I bet he could write software that would make it so as soon as the race is done, you will have the results of that. And the guy approached me and I said, yeah, I could volunteer to help with that. it really wouldn't take me that much effort to do that. So I created this software, and I actually created hardware too. I made this system that had a little chute that they ran through, and it had a laser beam. And when the laser got interrupted, it essentially like pressed the stopwatch automatically. And then what I did is I made software so when somebody ran through, they would just type in the number that was on the person's back. So somebody came in, it was number 42, type it in. And then since they were worried about a large group of people, I made it so it still worked with the spike idea. You pull off the paper just like you did it the old way, you stick it on the spike, and then the person operating the software would pull them off the spike and type them in. It would match them up, kind of like, so it was still the same process that they had before. It's just rather than writing the number on the stopwatch, they would type it in the number into the computer, and it would automatically associate it with a time. Beautiful system. Now, here's what went wrong. The thing that went wrong is I asked the guy running the race how many people would come in at one time and how many of those entries would build up on the spike before somebody started typing them in. And he told me something like, well, there could be large groups of people that come in. This was a fairly large race event. And so there might be large groups that come in, but there won't be any more than probably like 20, 25 of those on the spike at any given time. And I was like, so that's how you've traditionally done this. People are coming in, somebody's putting them on the spike, somebody's pulling them off the spike, somebody's writing them down. And so he's like, yeah, maybe 20 to 25. And so I thought, okay, cool. So what I did when I wrote my software is I statically allocated an array for times. And while I did not listen to him and do 20 to 25 spaces, I actually made it 200. I was like, well, that's like 10 times what he said would be on the spike. I'll set my array at 200, but I statically allocated it. And the problem with that is when somebody comes in, it uses a slot and it moves to the next one. When that one gets used, moves to the next one, so forth. Just increments up through the array in memory. And when somebody types in a number, it takes it back off and goes back down the array. But the array was statically allocated to have 200 times with 200 numbers at any given time. Now, I got it all set up and running. Everything was working beautifully. I waited for the first probably 50 people to come in the race, and I thought, cool, this thing is working. The guy that was running it was doing it right. The things were coming in. Somebody was sticking it on the spike. He was pulling it off the spike, and I thought, this is great. What could go wrong? So I tell him, I'm going to go inside, and I'm going to use the restroom. And I knew they had donuts in there. And so I was like, it was early in the morning. I was tired. And so I was like, I'm going to go inside and use the bathroom, and I'm going to get a donut. And so I'm inside. I ran into somebody, and I was talking to them. I was talking to them about how the system worked. They were all excited about it. They're like, oh, this is going to be great. We're going to have our results in like minutes instead of hours. And I was like, yeah. And I was explaining how it worked. And so as I'm coming out of the building, I look down to where the chute was set up. And I see the guy that was supposed to be taking things off the spike just talking to somebody else. He's just having a conversation. And I look at the spike, and the spike has a giant stack of runner numbers built up on it. And I'm like, that's way more than 20 to 25. That has to be like over 100 of those numbers. And I looked down the road, and you could see it was a straight shot into where the finish line was, that they're just like this giant mass of people coming down the road that are going to run through that gate. And when they run through that gate, the system is going to detect it, and it's automatically going to go to the next space in memory and add a time. So it's not even that the problem wasn't that he hadn't really typed those in. The problem was that the system automatically was going to go to the next space in memory. And here's what makes this problem even worse, is that since that was statically allocated, and C language does not bounds check arrays, if that went off the end of that 200 array of 200, then we were off writing times and events into places in memory that were not allocated for that array anymore. And so I go running across there to where the guys, I'm like, what are you doing? You're supposed to be typing these in. He's like, well, I just realized that since the software is doing it for us, I'll just wait till the end and do it all at once. It'll be more efficient. I'm like, no, you can't have, this cannot exceed 200 or bad things could happen. And so what happens is I tell the guy to start typing them in as fast as he can, and I start reading the numbers. But the glut of people coming down the road, they start going through the gate, and we're emptying them out. They're filling them up, and it actually exceeded the 199 index, and the whole program crashed. And now that the whole program crashed, you have people running through the chute and their times aren't getting allocated. Fortunately, I had told them to keep the printing stopwatch and keep pressing that just so we had a backup plan if something went wrong, because this is the first time the software had ever been used. And but now there was confusion because they weren't writing the numbers on the software. Well, fortunately, I wrote the software so it would log everything. Every time an event came in, it would save it to a file. So I had everything up until it crashed. And then we pieced it all together, but now it took longer than it did if they had just done the stopwatch version. So he had bragged to everybody and told them how they'd have the results instantly. And then at the awards banquet, after everybody was angry and tired and they didn't get the results for like 2 hours, he got up in front of everybody and told them it was my fault that it took so long because my software was written badly. And it wasn't really written, well, okay, in retrospect, maybe it was written badly, but I listened to him and he told me 20 to 25, and I said 200 ought to be plenty. And what I should have done is done dynamic allocation and made it so it resized that array automatically without having a set limit. And so, okay, so that's my programming horror story that hopefully will save you from the pain and embarrassment of having to stand in a room with 500 people that ran a race that are all angry at you and being told by the guy that ran the race, or that was the organizer of the race, that was your fault that they wasted their Saturday morning. And it kind of upset me because I volunteered that time and didn't get paid a dime for it, and had put in a lot of effort into that and listened to him with his 20 to 25 and then multiplied it by about 10. And it still was a problem. So the moral of that story is, A, don't listen to somebody when they say something like that. And B, always use something like dynamic allocation to ensure that that won't happen. Or at least if it does get to the point where it fills up, don't walk off the end of an array. Never allow your program to walk off the end of an array and start writing things into random memory. At least I should have stopped it there, popped up a warning, and just started saving the times to a file or something like that. There are a lot of things that the programmer that I am today would do much differently about that project, which would not have ever caused that problem. But I had to learn that lesson, and I learned it that day. All right, anyway, let's look at how dynamic allocation works in C. So the first thing about dynamic allocation is it's not built into the language itself. It is, however, part of the standard library. And remember, the standard library is something that every C compiler on every platform will have some version of. So these functions that we have down here, they're kind of universal. So if you're programming on Windows or Unix or a Mac or an embedded system, you're going to have some version of these functions, and they're going to work in the same way because it's a standardized library. All right, first one, malloc. Malloc allocates a contiguous block of bytes and returns the address of that block of bytes. In other words, it returns a pointer to that block. And remember how arrays are stored? Arrays are really just the name of the array by itself. By the way, it says the address of the beginning of a block of bytes in memory. So this malloc thing is going to be really useful for us to allocate memory. Yeah, that looks like an array, acts like an array, can be indexed like an array, but we can allocate it to be whatever size we want. Now, calloc or calloc works like malloc. The function parameters are a little bit different. We'll see that in a second. But the difference is this stands for a clear alloc. It allocates it and initializes the entire block to all bytes being 0. Malloc does not initialize it. Just gives you a block of memory. Whatever happened to be in it is in it. And there is kind of a hacking method called memory phishing or malloc phishing, where you could allocate big blocks of memory that the system just gives you, and there might be stuff left over from other programs running that could contain passwords that somebody typed in or other things. But calloc, it allocates it, initializes it to 0. Now, realloc can be used on a block that was allocated with malloc or calloc, and what realloc does is it changes the size of that allocated block. So it could be allocated to be larger or reallocated to be smaller, and it'll preserve the contents that were in there. So if we make the thing bigger, it'll add some spaces to the end, but it'll keep all the data. If we make it smaller, it'll make it smaller. It'll keep everything that's in there. We'll just lose the stuff that was on the end that gets allocated off. And then finally, free releases an allocated block. So if we allocate some block of memory, we should always free it. No exceptions. If you come to this from Python, you're probably not used to having to release things or free things. In C, we have to do that. If we allocate it, we have to free it. All right, let's look in a little more detail at those functions. So let's start with malloc. So malloc the way that works is you basically just pass in the size, and that's going to be in bytes. And notice there's this size underscore t type thing here. That's for cross-platform compatibility. So rather than using an int or a short int or a long int or whatever there, they just use size underscore t, and that's type deft somewhere in the compiler's standard configuration to be whatever the default unsigned integer. This is usually an unsigned int, like a 32-bit int for that. But if you're on a 64-bit compiler, it might be an unsigned 64-bit int. If you're on an embedded system, this might be an unsigned 16-bit int. But the idea is this is just an integer that says how many bytes we want, and that malloc is going to allocate that and return to us a pointer to that allocated block. If it fails because there's, for example, no memory left, there's not enough memory, then that's going to report a null pointer, a pointer value of 0 on the failure of it. Now, a quick example here, struct, bullet struct, pointer, bullet array. That's declaring a pointer, and it's a thing that can hold the address of bullet structures. And then we say bullet array, that structure equal, and then here we're calling malloc. We're passing the size of that bullet struct times 100, so enough space for 100 bullet structures. And then since malloc returns a void pointer, what a void pointer is, it's basically an address that has no type associated with it. And that's so we could use malloc to allocate blocks of integers or blocks of floats or blocks of structures of this bullet type. We can use it for any kind we want. So it returns just a generic pointer. But to avoid having a warning about assigning a pointer with no type to this bullet array structure, we cast that using a cast to a pointer type to a bullet structure. So this is going to allocate space for 100 bullets, just like we had when we statically allocated. But now notice, if we called this malloc thing, we could change this 100 to a different number, and we would get a different size block. Or if we used malloc, we could create it, fill it with bullets, and then resize it later to be a different size, bigger, smaller, as needed. And then here with calloc, it does the same thing, but notice that the parameters are different. We pass in a number of items and then the size of each item. So it does kind of that math that we did over here with multiplying the size of it times 100. It does that for us. And it also, remember, clears it out, but it works the same way. So here it is with calloc. We're saying I want 100 items. Each one is size struct bullet struct. And then we just cast that as that to use it. Now, the cool thing about this is that whether we allocated it with malloc or calloc, once we pointed this pointer at that, we can use it just like we would an array. So I can use square bracket notation to index into that and treat it just like it was an array that was statically allocated. Okay, realloc, we pass in the pointer, the address of the block of memory we want to resize, and then the new size that we want it to be. And it's going to reallocate that memory to be either larger or smaller, and it's going to return the pointer to that. So to use that, here's an example of using it down here. Here's the original malloc to allocate it for 100. And then down below, here's our realloc that's now changing it to 101. But I pass in the structure or the pointer to the block of memory I used before. I say, here's the new size. It's going to return to me a pointer to the one that's a new size. So it's going to increase the amount of space I have from 100 bullets to 101 bullets. So now I have a bullet array that is 101 big rather than 100. And I did that dynamically on the fly in my code. Okay, a couple final notes here on dynamic allocation, and then we'll do some example code. First thing here is always check for allocation failures, meaning that when you, and I did not do that in those examples earlier, that the allocation could fail and return a null pointer, you should have an if statement that checks that. You should also always free memory that you've allocated, because if you don't free allocated memory, like you have a function, let's say it dynamically allocates something, does something with it, and then exits, returns from that function without ever freeing it, then the operating system has allocated memory, the CPU has allocated memory for your program, and nothing ever told it it was okay to give it back, to let go of it. And that can create what's called a memory leak, where as the program runs, it keeps allocating memory that it never frees. It allocates more, never frees, it allocates more. And the pool of memory that's available for your program or other applications running on your system is eventually going to be diminished, so there's no memory left. So that memory leak can eventually lead to allocation failure or system problems with the operating system. Maybe you've seen that before, where you had a program with a memory leak where it runs for a while, and then your program or your operating system will say, hey, you're out of resources, or there's not enough memory to do this thing that you're trying to do in your browser anymore. And that's probably because of a memory leak. So any allocation you have, any malloc or calloc or realloc you do, make sure to call free on that. And make sure to check all control paths. So in other words, if you have a function that can return by an if statement and a function that could return down below with out an if statement, make sure you check every path that could exit that function. If you've malloc something in there, it needs to be freed, make sure you free it in every one of those control paths. Also, watch out for a logical misuse, meaning accidentally allocating something and then freeing it, or freeing it and then trying to use that. So you should always allocate memory, use the memory and or resize it, and then when you're done, free that block of memory. You should always do those things in that order. Allocate, use, free. Allocate, use, free. All right, let's quickly knock together some example code here that shows this in action. So I'm going to switch to, here, let me get code blocks up and running here. And then I'll switch over to the display so you can actually see this. And I'm going to code this live so you can see me kind of build this and put it together. All right, let me switch to where you can see code blocks here. All right, so here's code blocks. Let me resize this so I can fit it on the screen properly. Right about there. Looks good. Make it a little smaller. Put that right about there. And let me extend this down. Okay, that's about right. All right, so what I'm going to do is I'm just going to say File, New Project. And I'm just going to make this a console application. We're going to make it a C program. And I'm going to call this Dynamic Allocation Example. All right, so I'm going to start off, I'm going to go to my main.c here. Now, let me see if I can make the font size a little bigger. That might be a little bit helpful for you if you're watching this on a small screen. All right, so right about there. Now, what I'm going to do is I'm going to go ahead and start putting this code together. But the way that this code, I'm going to put it together is, I'm going to go ahead and take out at least this printf hello world. Well, actually, let me just change it. I'm going to change this to say like, hi score, list. And I'm going to make this program relatively simple, but what I'm going to do is let me go ahead and I'm going to make a while loop in here. So while 1, so that's going to run forever. And what that while loop is going to do, I'm going to print out a menu first. So let me do that first. So printf menu. I'll do \n. Let me actually put a colon on the end of that too. So that's just going to print the line menu, and then I'm going to print my menu items underneath here. So I'll do quote, and let's do an A to add a high score. And I'll put a \n and a semicolon. And now I'm just going to do another printf here. So printf, let's also have a way to print this high score list. \n. And let's have a way to exit. So printf, let's make that Q. Now this is not a particularly useful program right now, but I think it should be an example that gets the point across. This is going to run, it's going to print out the menu, it's going to ask us for input, and then we're going to read that input. So the last thing I'm going to do here, I'm going to do a printf I'll say enter choice, colon. And I'm not going to put a backslash in there because this is my prompt. But now after that, I'm going to go ahead and use a scanf. And I'm going to use that scanf to read in what they input. So space, and I'm going to do percent. Let's say this doesn't have to be very long. I'm just going to do 15 characters of anything other than a new line. So any character other than the new line up to 15 characters I'm going to gather. And this needs to be a format string. I forgot the quote up here. So there's my format string with anything other than that new line character. And now I needed to read that into a variable. And I'm going to go to call that variable input because that's what this is. We're just getting input from something. So up here at the top of my main, I'm going to make a character array called input. And I'm going to save enough space for 16 characters, one more than the number I'm reading in here to leave room to have the null character put on the end of it. Now, so now I have my input. There's one other thing we have to do with input because it's getting everything except the new line character. If there's stuff after the up to the new line, we need to consume all of the characters, including the new line. So we could do that in a number of ways. The way I'm going to do it here is I'm just going to make a while loop that says while. I'm going to call a function called getCharacter, getChar. And I'm going to say while getChar is not equal to \n. So in other words, I'm just going to read everything up to the \n and including the \n. And I'm going to make this an empty while loop there. I'll just put this on the next line. So that's going to clear out the buffer. And if we wanted, we could put a comment on that. So we read the input, we clear out the buffer, and now we're ready to check what they typed in. So I'm going to now have an if statement that says if. Now I need to check what they typed in, the string that they typed, in this case is input. I need to check input. I need to compare that with if that is equal to, in this case, the string just A. Now remember in C though, we cannot do a string comparison like this. And the reason being that input evaluates as an address of where that block of memory starts. And even this double quote string here evaluates as an address. So we're saying, is this address the same as that address? We don't want that. We want to check the contents of those things. So the way we compare strings is we use the string compare function. So I'm going to say, let's string compare input with the letter A. And the way we know, the way that when those match, that produces a value of 0. So if that's 0, those have matched. So now we're going to have what happens when we have A to add the string. So I'm going to put a comment here. Add a high score. Now I'm just going to flesh out the rest of this here. So I'm going to have an else if. And here I'm going to copy this real quick since this is the same code that I'm going to do for these other ones to have my other menu options. So else if string compare input with P. That's going to be the one for print. And let's add another else if, and the other one we need is Q for quit. Put a comment in here. And let's finish out the code for quit really fast here, because quit is going to be relatively easy. Basically, we just need to break out of the loop, but I'm going to add a print statement. So I'm going to say print f quitting \n. And then I'm going to put a break statement. And that break statement is going to be exiting that while loop. And after the loop, I'm going to put a print statement down here too, just so we can tell that everything is done. So here I'm just going to print out done. \n. Okay, so now we have our basic structure. So now what I need to do is add the code for printing and add the code for adding. So to do that, I'm going to need some way to keep track of that array, and I'm going to need some way to change the size of that. Now, if we were going to have other functions that dealt with this and looked at those high scores, we might want to store those in globals. So I'm just going to put those in globals right now. And also, since we're using that string compare, that's in string.h, so I'm going to go ahead and include that while I'm up here. But I'm going to go ahead and make my global variable now for keeping track of the high score list. And I'm going to need a structure to keep, I'm going to make a structure to keep track of that too. So I'm going to say, let's make a struct. Let's make it called high score struct. And we don't have to call it struct at the end. I'm just calling it that to make it clear when we use that later that that's a structure we're creating. And now I'm going to make the name of who has the high score. I'll reserve 16 spaces for the name. And I'm also going to store a value for the score. And let's just say it's integer scores. Maybe they could be negative, so we're just going to say int score. And maybe just to make this a little more cross-platform, I'm going to say I'll make that a long int to make sure we have plenty of space to store that. All right, so now we have our structure defined. Now let's actually make some variables for that. So struct, or our pointer to that, struct of type high score struct, a pointer, and I'm going to call this high score array. And I'm going to start that out as being null. So right now when we create that pointer to the structure, it is null, indicating that it's not pointed at anything. And I'm also going to need to keep track of a thing that says how big that array is. Since we're dynamically allocating, we're going to need to increase it when we add one, decrease it when we take ones away. So we're going to need to have a variable that keeps track of that. So to add that variable that keeps track of that, I'm just going to make a global, like an int here. So I'm just going to say int high score. Let's just call this size. Or maybe we could call it array size. But anyway, I'm going to set that equal to 0. Okay, so we have our code set up now, where now we just need to add the stuff that adds a score, add the stuff that prints the score. And so let me pause for just a second here, and then I'll be right back with you. And then we're going to finish out this code. So what I want you to do in the meantime is I want you to think about, maybe you should pause the video here too, think about what we need to do to allocate the memory, or we could even use realloc if we wanted to allocate the memory of the right size, that's the size that we need to store, to store this number of things. So when we add one, we're going to increment the size and then reallocate the memory for this high score array. And then we're going to add the values in. But before we do that, we're going to need to read in from the user, hey, what's the name you want? What's the score you want? All right, so think about how we would do that, and I'll be right back with you in just a second. Okay, so let's finish up this code. So where we left off, I'd left with the idea of like, well, what do we need to fill in here to add a score to our array? And what do I need to do down here to print it? So what I'm going to do is let's start with the add. So let's start with that first. So in order to add that score here, we're going to need some code here that first asks the user of the program. We want to ask them to type in a name, and then we're going to ask them to type in a score. So let's do that first. So add high score. So first thing is, well, how do we get them to type in a name? Well, we already have code that lets somebody type in something up here. So I'm just going to copy and paste this. So I'm going to copy that. I'm going to paste it there. I'll indent this to make the indentation nice. So now we're reading in whatever they typed into here, but we need a prompt first to tell them what they're typing. So I'm going to add a prompt before that. So print f. And here, I'm just going to say enter name. And I'm not going to put a \n because that's a prompt. We want it to fill in kind of right after that. And maybe I'll put a space there so it's not right against it. All right, so now we have them entering the name, and it's reading it into that input buffer. But I also want to read in a score, so I'm going to have another prompt, and another scanf. But this one, it's going to say enter score. And now to read something into an integer, I'm going to make an integer variable read in. So this one, I'm going to say my format is going to be a %d. And what I'm going to read that into is I'm going to need to have some sort of a variable that holds that score. I'm going to call it temp score. And the way that this works, since scanf has to change the contents of this temp score variable, we need to pass it by reference. In other words, we need to pass the address of that into that function. The reason we have to pass the address in there is because scanf is going to read in whatever we typed and it's going to fill that in. If we just passed it by value, scanf can never change it. So we need to pass a pointer in there. So in scanf, the things that we put in the that get filled in always have to be pointers. Well, input, notice we didn't have to put an address in front of that because input is the name of an array that's already an address, so we're good there. But this one, we need that. We're going to need to allocate that variable. So let's add that up here. So it's going to be an int. Let's make that called temp score. I think that's what I called it down here. Let's go check. Temp. Oh, let's put the underscore in there. Temp score. All right, so now we've read those two things in. So now we're up to the point where we want to add that to the array. But before we add it to the array, we need to increase the size of that array. So the first thing I'm going to do is I'm going to say high score array or high score size plus plus. So that's going to increment the size of the array. It started at 0. Now it's going to be 1. The next time I do this, it'll be 2. The next time 3. And now we need to reallocate how much memory was stored for that. And if I use realloc on a null pointer, it's the same as just using malloc. So here I'm going to say high score array equal, and now I'm going to call realloc. And the way realloc works, remember we need to pass in the pointer of the thing that we want to reallocate. So it's going to be high score array. And then we need to pass in the size. So in this case, the size is going to be the actual size of that thing. So high score size. But since this is in bytes, we need to multiply that by the size of a high score structure. High score struct. It needs to be struct. High score struct. Okay, so now notice what I did is I said take the size of each structure, multiply it by the number that there are, which is going to be 1 now, and then reallocate that and set that back to that variable. Okay, so we've reallocated that. And now the next thing we need to do is now copy the data into that. So the first thing I do, I'm going to go and set the score. So I'm going to say high score array subscript. And in this case, it's going to be the high score size. But we need -1 since indexes start at 0. So that -1 is essentially getting us up to the, or getting us to the last one. So high score size -1 gets us to the last element because they start with 0. And then we're going to say dot score equal, and then that temp score. So temp score. Now we're also going to copy the name into that. To do that, we're going to use string copy. So string copy into, so the destination is first, into high score array subscript high score size -1 dot name, comma. So that's the destination. Now the source is going to be what we read into up here, which is just input. So input, semicolon. All right, so now we've copied the two things in. We copied the score we allocated the array 1 bigger into the last one, the one that just got created. We're adding the score that they typed in. We're adding the name that they typed in. We're copying those into that. So now that last structure now has the new data added into it. And just for completeness, I'm going to print out a message here. I'm going to say printf. I'm going to say score added. \n. Okay, so now we have our code to add. And now let's add the code to print. Now the one to print is going to be easier because we don't have to reallocate or anything like that. We just need to make a for loop and go through this. Let's say for I equals 0 while I is less than high score size. Let's go and just do -1 and do less than or equal to make that a little more clear that we're going up to. We could have done less than just high score size. And then we'll do I++. So now we have our loop that's going to go through there. And before I go through this loop, I'm going to print out a little message that says what this is. So printf, let's say high score list \n. And when I go to print these out, I'm going to do a printf inside here. So printf, let's do a %d, which is going to be the index number. Let's do a \t. Let's do now a %s for the name, a \t, which \t, remember, is tab. And then let's do a %d for the actual score, and then let's do a new line. Now, so what I'm filling in is going to be I, the index number, which is going to start with 0. If we don't want that to start with 0, we want it to be like 1, 2, 3, 4. We could say +1 here. Let's go ahead and do that. Let's leave it as the index number. So it'll start with 0. And then here needs to be the name. So this is going to be high score array subscript I dot name. And then this one's going to be high score array subscript I dot score. Okay, so there we have printing out all of the things we need there. And I guess maybe one last thing that I might do here before we actually test this is maybe after this is done, let me print a couple of new lines after we print the table. I'll just do \n. And the reason for that is just going to be so I can space out so the menu isn't crammed right against that when the menu prints out when we come back to the top of the loop again. Okay, so now we have all of our code written here. Let's actually compile this and see what happens. Hopefully, I think I thought through all of that. Let's just run it and see if I have any compiler errors. And I do. Okay, I is undeclared. I use this variable I in this loop. So I'm going to go to the top of my function. Int I. We'll declare that. Let's try again. And we have a semicolon missing. Oh, I accidentally typed a comma there instead of a semicolon. So let's try again. Okay, now the program is actually running. So it compiled and ran. And so let's go ahead and do an A for add. So add, enter name. Let's add me. Enter score. Let's say I got like 100. Now let's do a P to print it. So there's the high score list. Just has one entry. So the array is just big enough to hold 1. Now let's add 2. So let's add another one, A. Let's add Jason. Let's give Jason 120. And let's add another one, Dwayne. Let's say Dwayne got a 90. Let's add, and let's say Jim. Jim got a 150. And now let's do a P to print them. And you'll notice now the table has Paul with 100, Jason with 120, Dwayne with 90, Jim with 150. Now right now, and he knows here the indices for this. So notice that this is going to grow that array to whatever size we want. No matter how many times I do this, as long as the computer still has available memory, I can add more of these. So maybe we add like a Travis. Let's give Travis like a 70. Let's add Ted. Let's give Ted like a 101. Let's add Joe 420. Okay, maybe we shouldn't do that. 40. And now let's do a P and print. Now notice that this is resizing that array by using malloc every time. Now there is one thing that we should probably add to this code, and that is, I said in the lecture, we should always check the return value of malloc or realloc to make sure that it actually works. So I'm going to add some code to do that. So up here, after realloc, I'm going to have an if statement. I'm going to say if high score array equal null, then that indicates a failure. We'll say the allocation failed. Let's do a \n, and let's say could not add new score. Now, this isn't going to come up when we run this, but we have now checked the reallocation there to make sure that, and we could do something about that. We could give them a chance to do something, but right now we just print out an error message. And notice what's going to happen here is if that did fail, we should probably also decrement the high score size back to what it was. And we should probably also put these things in an else so we don't try to add the score. So I'm just going to add an else here and say if it did not fail, then we go and add it and say we added it. And let's go ahead and decrement this back because adding it didn't work. So let's take that, which has already added one. We tried to reallocate, couldn't. And so down here, we take that one back off. Now that code, when we run this, is not going to actually do anything right now. The reason being, and let's just make sure it still compiles and runs. Or let's try our quit operation there. Quitting, done. All right. So let's go ahead and compile this again. That won't affect anything as far as how this is, unless we put so many of these in, we use up all of the memory inside of the system. But so now I can sit here all day, put in that, put in a score, add another one, put in a score, add another one, put in a score, print them. There's our table. We could do that all day long and add probably millions of these things to that table. Now, if we wanted to, we could add a little bit of code to this to maybe save that to a file. We haven't looked at file IO yet. We're going to be looking at that coming up in the next couple classes. But notice that you could make this save it to a file. You could make it save it to a file every time you add one. We could also add the ability to delete one. We say delete. It asks you whose name you want to delete or which index you want to delete. You put it in, and then it goes in, takes that one out of the array, moves all of the other ones up to fill in that one space, and then realloc one smaller. So deleting would be something we could add to that as well. But this gives you the idea of how allocation works. And there is one more thing we need to do with this code that is really important. And that is, if you remember, we said if we allocate something, we should free it. Now, right now, I'm allocating, I'm never freeing. So when I'm done with this program, I need to deallocate things right here. So I'm actually going to do that before the done here. So I'm going to say free. And in this case, it's going to be the high score array. And there we go. So now we make sure to free that so we don't have a memory leak where that uses it. Now, Windows will kind of protect us a little bit that if it's in a program like this, when that program exits, it'll free up all the memory that was allocated to that program anyway, in most cases. So it really wouldn't have hurt us not to have the free here, but it's a good habit to get into. If you malloc something or calloc something or realloc something, make sure to free it. Because if we had this inside of a function and it was doing that and not freeing it, we would, as the program ran, it would just consume more and more memory until there was no memory left. All right, so let's look at that code one more time here. Oops. So scrolling up to the top, we created our pointer variable to hold the address that malloc gives us to that block of data. We also kept track of the size. Down here, when we go to add one, we increment the size. So it went from 0 spaces to 1. We allocated enough space for one of those structure types of that. We store it in there, and we can access it like anything else. But again, remember how I said when you use that dynamic allocation, you should always allocate, use the thing, reallocate, and then when we're done, free it at the end. All right, so that's it for what I want to cover today. Let me go back to the slides quickly here. All right, so we wrote our example code, and really that's all I wanted to do today. So make sure to take a look at that example code. Make sure you understand what's going on there. Hopefully that live coding session kind of helps you get a feel for like how you go about writing code in C. I know some of you have struggled with that because it's different than other languages you've been in, but I'm going to try in the future, as I do these lectures, to spend a little bit of time like writing some actual code with you like that, so you get used to the kind of flow. And really, if I were writing this myself, I might write it a little bit differently, but using the things that you have learned so far, all of that code that we wrote there should have made sense. Maybe the casting was a little bit weird, where we took a void pointer and turned it into a pointer of the type we needed. But just note that that was to get rid of warnings that would show up. That void pointers have no type associated with them. If we're assigning it to some pointer that has a type, then the compiler will say, hey, are you sure you're not doing something wrong here? So we just cast it as the type of pointer we want. And that's totally fine, because it takes a void pointer that has no type and says, treat it like an address to this kind of thing, and then when I assign it, no warnings. Okay, so that's all we're doing today. So watch the other video, watch that one. And next class, what we're going to do is we're going to spend a little time talking about how to do some graphics. In C, we're going to use a library called SDL. So I'm going to talk you through how to get the project set up for that, how to get it to compile, and how to write some code for that. And then you're going to have a little lab where you're going to write some graphics code. And then from there, we're also going to then write a program that actually makes some graphical things. And if you combine graphical things with like dynamic allocation, now you're to the place where you can actually make something like a game with an arbitrary number of bullets and enemies that you kill and they disappear and other ones spawn and things like that. And dynamic allocation is a good way to do that. And the main thing is static allocation can work great, but you should always bounds check if you do that. Never go off the end of an array like I did on my race project fiasco. And hopefully my pain in that will serve to inform you. So if you're going to do static allocation, at least bounds check. If you're not going to do static allocation, do dynamic allocation. Make sure you always free things so you don't have a memory leak that eventually causes problems later. And make sure that you follow that. Allocate, use, reallocate, and then eventually free. Okay, that's it. And I'll see you guys soon.